We're going to talk about multiple topics today. The first of which is source combinations. So let's start with something fairly straightforward. Voltage sources in series. So how many of you have ever had to change the batteries in a remote control? You have all applied voltage sources in series if it required more than a single battery to do that. Okay. So if we have a system like this, where we have some voltage source, let's call it VS1, some resistor R, some second voltage source VS2, and let's say for the sake of argument here, a third voltage source VS3, like so. This would be an example of a single loop circuit. And so I'm arbitrarily going to decide that there is some current flowing in the clockwise direction such that there will be a voltage drop across our resistor, which I'll call VR, positive polarity on the left, negative polarity on the right, so that the resistor is absorbing power. If we write a Kirchhoff's voltage law equation around this loop, what we will find is we'll have negative VS1 plus VR plus VS2 plus VS3 is equal to 0. And now I'm going to move my resistor voltage drop to one side of the equal sign and all of my source voltages to the other side. So that's going to look like VR is equal to VS1 minus VS2 minus VS3. And from the perspective of the resistor, it sees an equivalent voltage source VEQ, where VEQ is simply the combination VS1 minus VS2 minus VS3. So we can glean a couple of things off of this simple picture here. The first is that when voltage sources have the same polarity, so when the current hits the positive polarity terminal first, those guys get the same sign, and when the current has the opposite polarity, some subtraction or something like that is going to occur here. So because polarity terminal of VS1 first and the positive polarity terminal of VR, that's why VS1 is going to wind up having a positive sign in our equation. And because we see the opposite polarity first for VS2 and VS3, it's why it gets the other sign. So effectively, voltage sources of the same polarity will get combined together or added together. Voltage sources of opposite polarity will be subtracted. Those are the rules for combining voltage sources in series. Now let's talk about voltage sources in parallel. So voltage sources in parallel is something that you will see a lot in certain industries, particularly those dealing with photovoltaics or solar cells and things like that. Okay? So you might often see strings of solar cells wired together in parallel. And the reason why a string of solar cells might be wired together in parallel is so that they're able to supply a large amount of current while restricting the voltage to some specific limitation, okay? In our class, we're not going to see voltage sources in parallel after today, but we do need to talk about a couple of limitations as to really why we are not going to see them, okay? So let's consider this simple circuit. And I'm going to use numbers on this one. Let's say that I have a 5-volt source, a 10 ohm resistor, and an additional 5-volt source. And they're all connected in parallel like so. What's the voltage drop over my resistor? Not a trick question. 5 volts. Great. So when our voltage sources have the same magnitude and the same polarity, all of our basic circuit analysis techniques work out great. Now, let's completely ruin this. And make this one 5.1 volts. What's the voltage drop across our resistor? I see what you're doing there, taking the average, but I disagree. So let me explain why I disagree. Law equation around this loop, we would see that VR is 5 volts. If we write a Kirchhoff's voltage law equation around this loop, we would see that VR is 5.1 volts. How can the voltage drop across that resistor be two different things simultaneously? It can't, okay? Whenever we have a situation like this, our circuit analysis fails. And the reason that it fails is because it's not taking into account any resistance that the wires that are connecting things might have. So we could absolutely take a fully charged AA battery and a slightly discharged AA battery and a resistor and put all three of those things in parallel, and we wouldn't, I don't know, rip a hole in the universe or anything like that. We might cause a couple of sparks as the battery's charge tries to balance itself out. But from an ideal case, which is what all our circuit analysis is based on, we've broken the rules here. Because the Kirchhoff's voltage law equation around the outside loop says that -5 volts plus 5.1 volts is equal to 0, which cannot be true. So if we ever see voltage sources in parallel and our KVL equation is broken, we cannot do any further circuit analysis on that whatsoever. We have to stop and set it aside, okay? Is that clear? All right, now, honestly, you won't ever actually see that in a circuit analysis class or anything like that, unless somebody other than me is just being a real jerk, okay? All right, now let's move along to current sources. And we'll start with current sources in parallel. So let's call this IS1. Here's a resistor. Call this IS2. This guy IS3. All connected in parallel. I am going to assume that there will be a voltage drop across all of these elements in parallel. That's common to everything. And I've oriented my voltage in such a way that I'm going to have a current I. Resistor is absorbing power in this system. If if I write Kirchhoff's current law equation at the top node, where currents entering the top node are positive, what I will get is IS1 minus IR minus IS2 minus IS3 is equal to 0. And I can rearrange this by putting the resistor current by itself, giving me IR is equal to IS1 minus IS2. Sorry, this should be plus IS3. My apologies. And so IR sees an equivalent current source, IEQ, that is simply IS1 minus IS2 plus IS3. And the rules here are fairly similar to what we saw with our voltage sources. When current sources are in parallel, if they're in the same direction, they add together, and when they're in the opposite direction, they subtract. Fairly straightforward, right? Now, let's deal with current sources in series and see how easy it is to break that system as well. So let's consider a simple system where we have 3 amp current source in series with a 5 ohm resistor in series with another 3 amp current source. Here is our resistor current, IR. When the currents are of the same magnitude and the same direction, both of them are driving current clockwise around this loop, everything works out great, and the resistor current is simply 3 amps. However, if the currents are slightly different, or in any way different, actually would be a better way to put it, Kirchhoff's current law will break down, right? If we apply KCL at this node, IR is obviously 3 amps. If we apply KCL at this node, IR is obviously 2.9 amps, and it can't be both simultaneously. Did they turn the volume down, or did I need to go yell at them? Okay, that was aggressively. All right, so effectively, current sources in series, you have to be careful and make sure that everywhere around the loop is carrying the same current, or else Kirchhoff's current law breaks down and we can't do any subsequent analysis. All right, so this was fairly straightforward and pretty quick. Now let's get to something, in my opinion, a little bit more difficult, but a lot more useful. We are going to now talk about the concepts of voltage division and current division. So these are shortcuts that we can use in our circuit analysis in very specific instances. Okay. All right, so let's say that we have a series combination of resistors. R1, R2, out to R sub n. And let's say, for the sake of argument, that this series combination of resistors is part of a larger circuit, okay? Where we know the voltage drop across that series combination of resistors. What we're interested in, the voltage drop across an individual resistance. So VR1 or VR2 all the way out to VR sub n. All right. Since we have a known voltage and a series combination of resistors, there should be some current I that's flowing through all of those resistors, and I has to be the same for every one of those resistors because this is a series combination of elements. So we're about to derive something, and it's going to start off looking startlingly like what we did in class on Friday. Okay. We can write around this path. And in doing so, what we would find is that our known voltage, V known, is simply equal to all of the voltage drops across the multiple resistors connected in series. Using Ohm's law, we can express all of those voltage drops in terms of that common current I. And we can factor out I so that we'll have I times the combination of R1 plus R2 all the way out to R sub n. And here's where we're going to do things ever so slightly differently. We're now going to rearrange this guy and solve for I. So I, in this case, is just our known voltage divided by R1 plus R2 all the way out to R sub n. So knowing what I is, we can then say our voltage VR1 is just I times R1 using Ohm's law. Substituting in our value for I, what this looks like is V known times the ratio of R1 over R1 plus R2 all the way out R sub n. Similarly, VR2 would just be I times R2, or V known times R2 over R1 plus R2 all the way out R sub n. And hopefully by this point, the pattern is pretty obvious. For any individual voltage drop across any of these series resistors, it's just a ratio of the known voltage over the entire system multiplied by the resistor we're interested in divided by the equivalent series resistance. V R sub K, where K is, or excuse me, K is just the arbitrary index of the resistor that we're looking for, is V known multiplied by the ratio of R sub K over R1 plus R2 all the way out to R sub n, or in fancy mathematical notation, this is going to be V known multiplied by the ratio of R sub K over the sum from I is equal to 1 to N of R sub I. Or third simple formulation here, RK over REQ. So let's play around with this and introduce some rules for using voltage division. So let's say that I have an 8-volt source connected to the 10 ohm resistor, 6 ohm resistor, and an 8 ohm resistor. And the first thing that I'm going to look for is the voltage drop over the 10 ohm resistor. Using our voltage divider relationship, we can see that V10 is just going to be 8 volts multiplied by 10 ohms over 10 ohms plus 6 ohms plus 8 ohms. So that's 8 times 10 over, let's see, 10 plus 6 plus 8 comes out to be 10/3 of a volt. We didn't actually have to solve for the current or anything like that. The voltage is given to us simply by that ratio of resistances. Okay. Now, let's mess things up ever so slightly. What if we want doesn't look particularly different, but there's something important here that's happening. You're exactly right. All you have to do is add a negative sign because we're seeing the negative polarity terminal first as we're following our imaginary current around that loop. 100% correct. You guys are getting it very, very quickly. So V8 in this case is going to be 8 volts multiplied by 8 ohms over 10 ohms plus 6 ohms plus 8 ohms. But then we need to make sure that we include this negative sign out front. So that's going to look like negative 64 over 10 plus 6 plus 8. Negative, let's see, multiply that by 3. Negative 8/3 of a volt. To be very, very clear, because someone back there, I can't recall exactly who, was rather astute and said that all we're going to need to do is add a negative sign here, but I'd be willing to bet there are a couple of you who are not entirely sure where that negative sign came from. So I'm going to scroll up here. When we derived the relationship for voltage division, our known voltage is of the opposite polarity as all of our resistor voltage drops, right? So if we follow that current I around, I sees the positive polarity terminal of all of the resistor voltage drops. And if it came up through that known voltage thing there, we'd see the negative polarity terminal, okay? If we follow I around this loop, it sees the positive polarity terminal of the 10 volts of the voltage drop V10. So it gets a positive sign, but it sees the negative polarity terminal of the voltage V8, which was where that negative sign is coming from. Effectively, with that polarity, there's no way that voltage V8 could be anything other than negative, since the resistor has to be absorbing power because it is incapable of supplying, okay? So that's just something that you need to be aware of here, okay? It's following the exact same rules that we established for Ohm's law, which somebody was nice enough to write up here on the board so I can just point at it. But effectively, if our current is flowing into the positive polarity terminal, we get a positive sign. If the current flows into the negative polarity terminal, we get a negative sign. Regardless of whether we actually care or calculate the current at all. All right, so if all the circuits that we were going to deal with were single loop circuits like this, voltage division would save us a bunch of time, okay? However, there are going to be circuits that we can apply voltage division to that don't strictly fit this criteria, all right? So let's consider this circuit. I have a 5-volt source, 20 ohm resistor, a 9 ohm resistor, and a 6 ohm resistor. And we want this voltage, which I'm going to call Vx. So when we derived our relationship for voltage division, we did so using a simple series combination of resistors. In fact, that's the only time we can use voltage division, when all of the resistors are in series. So if we wanted to adapt it to a problem like this, we need to figure out how to make this look like a series combination of resistors. Anybody have any thoughts on how we might do it? Daniel. Exactly right. So we can just treat the 9 ohm resistor and the 6 ohm resistor in parallel as a single equivalent resistance and then apply voltage division. So I'm going to do that all in one equation. So we could say that Vx in this case is going to be 5 volts multiplied by 9 ohms times 6 ohms over 9 ohms plus 6 ohms divided by 20 ohms plus 9 ohms times 6 ohms over 9 ohms plus 6 ohms. And I'm willing to bet that at least a couple of you guys, those who are caught up on their homeworks, were probably wishing they would have known this about 2 days ago. So let's throw this in the calculator. 9 times 6 is 54. I think 9 plus 6 is 15. You're going to get that feeling a lot in this class, unfortunately. 45 over. We'll ask you to do something, or the homework will ask you to do something the hard way, and then literally the next class meeting, you will find out a slightly easier way to do it. All right, so this is voltage division. How are you guys feeling about this? Hopefully it seems fairly straightforward, because in truth it is. Okay. Now, yes, Ryder. So if you go back to our notes from Friday, I am just using the equation for 2 resistors in parallel, right? So whenever you have 2 resistors in parallel, you could say it's 1 over R1 plus, or 1 over R1 plus 1 over R2, but that is the same as R1 times R2 over R1 plus R2. So that's that shorthand that I warned you I was going to use. I'm going to use it a lot. Yeah, so that's where that came from. No problem. Any other questions on this? Questions are good. Nick. Okay, so there's a couple of problems with your thought process there. The first is that you're assuming that the voltage drop over the 9 ohm resistor and the 6 ohm resistor would be different, which is not true because they're in parallel. And secondly, and this is a new concept, so that's why I'm talking about it here, voltage division only works for series combinations of resistances. So you could not arbitrarily ignore the 9 ohm resistance and write your KVL equation around the outside loop, because that would effectively be saying, I don't think any current flows through the 9 ohm resistor. Or you couldn't write it around the, write a voltage division equation around the inside loop, because that would effectively be saying, I don't think there's a voltage drop across the 6 ohm resistor or any current flowing through it. You have to take into account both. And we're developing an equation like we're doing here, and forcing voltage division to fit into this circuit by treating those two parallel resistances as a single equivalent resistance, so that I have a known voltage of 5 volts over a series combination of resistances.
So Vx is the voltage drop over the 6 ohm resistor?
Yes, but it's also the voltage drop over the 9 ohm resistor because they're in parallel. So it has to be the voltage drop over both. Any other questions regarding voltage division? Questions are good. It means you're trying to learn. All right. So if there are no other questions regarding voltage division, then let's talk about current division. Once again, we're going to have something here that looks extraordinarily similar to what we did on Friday, and then we're going to take a slight subtle turn here. Okay. So let's consider that we have a network, and it can be part of a larger network that contains multiple resistances in parallel. So let's call this guy R1. This guy R2. And this guy R sub n. If we have a known amount of current flowing into this combination of resistances, we can assume that there is going to be some common voltage drop across all of the resistors because they're in parallel. Actually, I'm using the wrong color there. I'll do that. Just to be consistent with the color scheme that I used on the last thing. And we can say that each of these resistors is going to carry its own current. So effectively, current division is going to help us develop a relationship that tells us how this known current splits or divides between all of these resistors that are connected in parallel. Okay. So if we apply Kirchhoff's current law, we know that our known current, I known, is simply going to be IR1 plus IR2 all the way out to IRN. And we can express all of these resistor currents in terms of our common voltage V, such that this looks like V over R1 plus V over R2 all the way out to V over Rn. And factoring out V, we get 1 over R1 plus 1 over R2 plus 1 over Rn. Solving for V, this becomes I known divided by sum of the reciprocals of the resistors. So now that we know V, we can substitute in this relationship to solve for our resistor currents. So IR1 is just V over R1. I'm going to write this very slightly differently. V multiplied by 1 over R1. And from here, what we're going to have is I known times the ratio of 1 over R1 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. We could do something similar for IR2. Or this would simply be V over R2 or I known multiplied by 1 over R2 divided by 1 over R1 plus 1 over R2 all the way out to 1 over Rn. And you guys could all kind of see the pattern now, right? So in general, the current flowing through the kth resistor is going to be the known current flowing into the network of parallel resistors multiplied by a ratio. That is 1 over R sub k divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Notation. This looks like 1 over Rk divided by the sum from I is equal to 1 to n of 1 over Ri. And in a different notation, this looks like the equivalent parallel resistance divided by the kth resistor. All right, so this is the formula that I prefer. Okay. The reason why I prefer this particular look is because it's the closest that we see to voltage division, which is a fairly easy to understand concept, okay? The resistor that we're interested in is in the numerator, and all of the resistors in parallel are in the denominator. But when we're doing current division, we deal with reciprocals. When we're doing voltage division, we just deal with the resistors by themselves. Now, there is an alternative definition for current division that anybody who's repeating this class and didn't have me as their instructor is probably aware of. And in my opinion, that alternative definition for current division is hot garbage, okay? I'm gonna write it down. It only works for 2 resistors. And then I'm gonna explain why I feel it is hot garbage and you should use my thing. And it is not purely because I'm very, very conceited, okay? So, for 2 resistors in parallel, and only 2 resistors in parallel, we could say that IR1 is I known times R2 over R1 plus R2, and IR2 is I known times R1 over R1 plus R2. So the reason why I think this is garbage is because the quantity in the numerator is not the resistor that you're actually trying to find the current through. It's the other one. This works and is simple, but it is confusing, right? It looks real nice and pretty. It looks extraordinarily similar to what our voltage division equations look like, but it is unnecessarily confusing because you have to take the resistor that you don't want and throw that in the numerator. So that's why I really, really do not care for this. Now, I will give you fair warning that in my solution to some of the old test problems, I have used this formulation of current division, okay? I have not yet gone through and updated those solutions to use this other one that I believe is fundamentally better. I would absolutely encourage you guys to use the one that uses the reciprocals, at least until you get very, very comfortable applying current division. Then you could branch out to the simplification for when there are exactly two resistors in parallel. One other thing that I want to point out here is that these two at the bottom literally only work for two resistors in parallel, whereas the one that we derived up top that I've circled in green or boxed in green works for any number of resistors in parallel. So it is more powerful. It is closer to what we expect to see from our very brief knowledge of voltage division and things like that. All in all, I feel it is a much, much better and more sound means by which to perform current division as part of our circuit analysis. Okay. All right, so let's work a couple of examples here. Let's say that we have a 3 amp source, and then we have the 6 ohm resistor here, a 9 ohm resistor here, and a 12 ohm resistor here. And let's start by solving for the quantity I6. Using current division, just directly applying it from the equation that we just derived, this is going to look like 3 amps times 1 over 6 ohms divided by 1 over 6 ohms plus 1 over 9 ohms. Now we can throw this in our calculator. I get 18/13 of an amp. What if I were interested in this current I12? How would our current division equation change? You would put a negative in front of it. And the reason is the current is flowing in the opposite direction from what we established earlier. Another way to think about it is that we're expecting voltage drop across all of our elements in parallel to have this polarity, positive polarity on top. So we're expecting our source in this case is supplying power to this system. And so all of the currents as they split should be flowing down through the resistors. Because that current I-12 is flowing up, it's in the opposite direction that we expect, it gets a negative sign. So 3 amps times 1/12 over 1/6 plus 1/9 plus 1/12. Negative sign out front. I talked about it and then almost forgot to do it. And I get 9/13 of an amp. Yes, Daniel. -9. All right, fantastic question. Let's do just that. So let's say that we had a 5 amp source, 4 ohm resistor, 3 amp source, and we wanted to know this current I. Is this a situation like you were describing? Great. All right. So the first thing we're going to do here is we are going to combine current sources, right? We have 2 current sources in parallel, so we can combine them together. So the question here is, do we want our resultant current source to be direction up or direction down? Direction up, okay. So if we have 5 up and the 3 amps is in the opposite direction, then we are going to combine those 2 together, and it would make 5 minus 3, which is 2 amps up, and we would eliminate the 3 amp source down. If we had gone the other route and we wanted our current to be down, we would have had 3 amps minus 5 amps. We would have -2 down, which is the exact same thing as the +2 up that we got here. So we can't do it wrong as long as we're recalling that when they're of opposite signs, subtraction occurs. So from here, this is just a direct application of our equation. I4 is going to look like 2 amps times 1/4 over 1/4 plus 1/8. Because the current is going in the opposite direction that I expect, I put a negative sign out front. And so I get -4/3. Jonathan.
You had added extra before we covered into 3 and 5, and you had added a resistor in series into the parallel circuits.
We could not have combined the current sources, and therefore current division would not be the analysis tool that we're looking for.
So you could try to combine anything.
Okay, so what you are suggesting, here we had our 5 amp source. Let's say that we had a 10 ohm resistor. And this was our 4 ohm resistor. This is our 3 amp source. And this is our 8 ohm resistor. Something like this, right? So the only combination that we could make right here with our current level of circuit analysis knowledge, and I have to say that because we will learn something to do in like later on next week that could mess around with this a little bit, would be to combine the 4 ohm resistor and the 8 ohm resistor. But that would not in any way, shape, or form help us figure out what the current flowing through the 4 ohm resistor is, because we generally speaking would want to leave that one alone since that's got the quantity that we're interested in, right? If we were trying to solve for this current I4, as soon as we lump the 8 ohm resistor and the 4 ohm resistor together, I4 no longer exists. So for a circuit like this, we would have to fall back on KCL, KVL, and Ohm's law for literally, I don't know, 2 more class meetings until we learn things like nodal analysis and mesh analysis and all that kind of stuff. We'd have to use a combination of analysis techniques to brute force our way through this. But let's take your thought here and play with something slightly different. All right, so just to be clear here, cannot use current division. What if we had something like this? I would argue that we can use current division here, even though there are series resistors and things like that that we have to concern ourselves with. So let me explain what I mean. How much current is flowing through the 4 ohm resistor? All 5 amps, right? So this 5 amps of current that leaves our source flows through the 4 ohm resistor, and then it sees 2 branches. One directly down that has a resistance of 6 ohms, and one to the right that has an equivalent resistance of 10 ohms. So it sees, in essence, 2 resistors in parallel. And so we could use current division to figure out how much splits off and flows just through the 6 ohm resistor. Our equation for that would look something like this. I6 is equal to 5 amps times, and here we're going to have 1 over 6 ohms because the branch that we're interested in has a resistance of 6 ohms. And then 1 over 6 ohms plus 1 over 2 ohms plus 8 ohms. We're treating that right-hand branch that contains the 2 ohm resistor in series with the 8 ohm resistor as a single 10 ohm resistance from the perspective of our current. Okay. And so this is going to look like, let's see, 1/6 plus 1/10. 25 over 8 amps. If we wanted the current flowing through the 8 ohm resistor, how would this change? So if we wanted this current, we would just take this guy and move it to the denominator. Or excuse me, the numerator. Be the exact same effective equation. But we need to make sure that even though we're trying to find the current through the 8 ohm resistor, we're really trying to find the current through that branch that happens to contain the 8 ohm resistor. So it wouldn't just be 1 over 8 ohms, it would be 1 over 2 plus 8. Okay. It does not, right? So Kirchhoff's current law tells us that if the current flowing in here is 5, current flowing here must be 5, and the current flowing in from the left is the same, right? So effectively that resistor current passes through it. It will cause some voltage drop to occur over it, but it's not going to restrict the current in the way that you're talking about, if that makes sense, right? So one of the fundamental tenets of circuit analysis is that the current flowing around a single branch has to be the same at all points along that branch. Any other questions? All right, so I think I've talked about enough stuff for today. So we do have an in-class assignment. I didn't get around to putting it online until early this morning, so I went ahead and printed off several copies. I saw some of you walking out to print off your own copies and all that kind of stuff. But if you didn't get a chance to do that, I apologize, and I brought some for you.